Now that we already have the introduction to alkenes and alkynes done with, also with their structure in the IHD, let's go with the reactions of alkenes and alkynes, or the reactions of unsaturated hydrocarbons. So let's have an example alkene here, and I will analyze its structure just briefly. This is ethene again, or its trivial name ethylene, and we have here one sigma bond, but what's more important is one pi bond. So of course we know that the chemical bond is comprised of electrons. Then most likely, if we're going to pick between a nucleophile and an electrophile which would attack this pi bond, of course we will choose the one that likes electrons, and of course that would be electrophile. Alright, so if we're going to write down its mechanism, it should be electrophilic. Now the other is the scheme. What is the scheme? Is it addition, elimination, or what? So let's try adding a certain reagent on now. Let's say that the electrophile is, or the reagent in complete structure is also chlorine. Chlorine can only have a nucleophile and an electrophile by a heterolytic cleavage, so this should be able to form a positively charged chlorine and a negatively charged chlorine. Of course, since these are electrons, the first to attack would be this one. So what happens? Since this one has no electrons, let's say that this carbon would use these electrons to form a bond with this chlorine. So what results? Wow, markers fly now. Right. What happens is, since this carbon is going to use these electrons, the pi bond would be broken and would be sacrificed for bonding with this. So we see that this is the electrophile. This reacts first. That's why it's electrophilic in the first place. Now what happens? This carbon, look here that this carbon has its electron. This is supposed to be its electron, right? The electron of this carbon was used, so it lacks an electron now, so it should be positively charged. And since we have here a negatively charged chlorine, this is the second one to react with this carbon. And so as a result, the final product would be both chlorine molecules would bond to the alkene. Alright, so in short, you actually just add both of these chlorines to the alkene. And so look at this, you only have one product. You have this is the first reactant, let's designate that as A. This is the second reactant, or the reagent, and then you just combined A and B together. So again, what is A plus B yielding AB? It's not elimination, it's not substitution, and of course this is addition. You just added them together. So the final, or the mechanism of alkenes and alkynes, since alkynes have pi bonds also, is electrophilic addition. Electrophilic addition. Forget that, and I don't know, probably I'll curse you for the rest of my life. Alright, just kidding. So that's the general reaction mechanism for alkenes and alkynes. Now let's go over the specific reactions one by one. So probably I'll put ethene at the center, and then let's discuss the reactants one by one and the reaction types one by one. So if the reagent we are using is simply hydrogen, what's the product? Again, what happens is, at the end we simply add the two halves of the reactant to each carbon. So it's as if we divide this by 2 and then we distribute it between the two carbons. So the product here is simply an alkane. hydrogen cannot react by itself. It's not as if there's a hydrogen molecule there and it's going to react, because it's relatively unreactive. So you use a catalyst, a metal catalyst such as platinum or palladium. This is now called catalytic because it is catalyzed, hydrogenation because you add hydrogens. It's that simple. Now, what if instead of hydrogen we use a halogen, and we have already seen this as the example previously. So here, this is simply halogenation. Alright. If ever you see something like DCM, which is dichloromethane, or CCl4, these are just solvents. They are not actual reactants in the reaction. So we know already the drill. We copy the original structure, then we just add the two chlorines. And here, we form a dihalide. Dihalide meaning two halogens in a hydrocarbon. But here I would like to put a note. A dihalide or a diol. Diol is for alcohols or ones with OH. Can either be vicinal or geminal. So if we use locants, vicinal is actually 1, 2. Geminal is 1, 1. Let's have an example. This is vicinal. Why? Because one of the chlorines are put in carbon number 1 and one of them in carbon number 2. This is vicinal. Alright. While here, let's draw an example of a geminal dihalide. This is a geminal dihalide because both of the chlorine molecules or atoms are in carbon number 1. So this is geminal. And look at the structure again of this dihalide. This is placement in 1, 2, so this should be a vicinal dihalide. Alright. What if we have a mixture of a hydrogen and a halogen? And actually, for example, let's just use HCl. Okay, so we just combine their names. We have a hydrogen, so hydro, and then a halogen, halogen. So the reaction name is hydrohalogenation. And again, we draw the same thing, H and Cl and the other. And this one is, well, we know this is a simple haloalkane or alkyl halide. Now I would like also to introduce another principle in this. If for example this one is asymmetrical, this one, we say that this one, hydrogen and chlorine, are symmetrical because if you divide that into two, hydrogen, for example hydrogen, it would yield both hydrogens if you cut it, right? Just one positive and one negative. Also for chlorine, when you cleave it, you have two chlorines, only difference is charge. But if you have HCl, you produce two different products. One is H positive and one is Cl negative. And if we have an asymmetric reagent, we're going to take note of one rule, and that rule is known as Markovnikov's rule. Alright, cool name. Alright, so Markovnikov's rule states that, in a general nutshell, people would say, richer gets rich, poor gets poorer. What do I mean? We are talking here about the abundance of hydrogens in the vinylic carbons. For example, I use this geminal dihalide. Which of these is richer in hydrogen? Would it be carbon number 1 or carbon number 2? In carbon number 1, we only have one hydrogen. But here in carbon number 3, no, carbon number 2, my god, we have 3 hydrogens. So that means that, for example, we add HCl, alright, H goes to this carbon and Cl goes to this. Let's have an example. This time, let's use an actual alkene. For example, I have this one. And I add HBr. What happens? Since here, in this carbon, we only have 1, and in here, we have 2, where does H go? It goes where there is more hydrogens. So if we draw it like that, we have both hydrogens. Wherever there is more hydrogen, we put the hydrogen there. And wherever there is less hydrogen, we put the other half there. So if we have 1 chlorine here, 1 hydrogen, the bromine also goes here. So the richer gets rich, the poorer gets poorer, or at least they just maintain the same number of hydrogens, right? Because here we have 1, we have 2. Now the rich get richer, and here the poor remains poor. Alright, so I hope you understand that. Anyway, this is just a review. Now, what if we add water, H2O? Actually, if you divide H2O, you get H plus, right? H positive and OH negative. And this should be in the presence of acid. That's why, for example, it's either they use this notation H2O plus H plus, or you combine them together to form H3O. It's just the same. So if you add water to an alkene in the presence of acid, well, let's just draw the product first. One would be H, right? And the one would be OH. What do we get? This is the hydroxyl functional group, and of course, the class of organic compounds with that group are called alcohols. So meaning, hydration, because we add water, hydration of an alkene would yield an alcohol. Alright, so that's why they say alcohol is never the answer unless you hydrate an alkene. Corny. Anyway, now, next is what else could be a reaction? Alright. There is a certain type of hydration which is special. Alright? I'll tell you why. So, but it cannot be used on ethine. So let's just write the name first. Hydroboration. Okay. Hydroboration followed by hydration. And we will discuss this in a separate paper perhaps. Here we should be able to recall Marconikov's rule. Again, Marconikov's rule states that the richer gets rich, the poorer gets poorer. Or the carbon with more hydrogens gets more of the hydrogen, and the carbon with less hydrogen will not get the hydrogen. For example, I have this. If we are going to hydrate it, right, H2O, what happens is that 1 carbon gets the H and 1 carbon gets the O. H. So which one should have the H? Since this carbon has more hydrogens than this one should get the H, right? And this one should get the OH. This is a Marconikov's product because we follow the Marconikov's rule. But if we use the reagents for hydroboration, and that is comprised of borane, tetrahydrofuran, a base, and a peroxide. It's a lot of reagents, right? Anyway, what we would get is actually the reverse of this, and we call that an anti-Marconikov product. So here again, if we're going to follow the Marconikov's rule, this carbon should get the hydrogen because it has more hydrogens. But in hydroboration, this is the opposite. So we get the anti-Marconikov product. So I'll just put a dot to say that we have discussed this already. Now, let's talk about epoxidation. So in epoxidation, you actually form an epoxide, and an epoxide is something like this. Alright? So where did we get this? So let's draw this in detail. If we epoxidize this, we have this, then we link these two carbons by an oxygen. Where do we get the oxygen? From the reagent, which is a peroxy acid. Alright? It's a peroxy acid because it has an additional O. Alright? So here we form an epoxide, and if we hydrate the epoxide, what happens is that, look, this is the original epoxide, right? The oxygen will go to one of the carbons. Since we have H2O here, let's put the H here and the OH at the other. Now what do we get? We get a vicinal diol. Vicinal again because it is located, the two hydroxyl groups are located in carbon 1 and the other in carbon 2. Alright. So these are the simpler reactions, including the principles of Chronicles Rule and vicinal and geminal diols or dihalides. Let's now proceed to a special case, and let's draw again ethene. Potassium permanganate is a special reagent because it can allow an alkene to undergo two different types of reactions. The difference would be if the environment is acidic or basic. For example, we have a basic environment here, and this is acidic environment. If we have a basic environment, we call this mild oxidation. Alright, I denote oxidation as O in brackets. This one is strong oxidation if we have an acidic environment, or its other name is oxidative cleavage. It's not the other meaning of cleavage. Alright, so the mild oxidation is quite simpler. So in mild oxidation, you actually just, in a nutshell, in a simplified way, you just get a vicinal diol. But in oxidative cleavage, it is quite different. I would say that from ethene, you get 2 moles of carbon dioxide. And you may be wondering, where the hell did these oxygens come from? So let's discuss the rules on oxidative cleavage, or the way that I usually teach how to predict cleavage products. So look at the vinylic carbons here. Each of these carbons are supposed to be bonded to a maximum of 2 hydrogens. But there could be a case wherein a carbon has only 1 hydrogen attached to it because the other is bonded to, the other bond is with a carbon. There is also another case wherein this carbon has no hydrogen bonded to it because both bonds are used up for a carbon to carbon bond. Now, this is a general guideline. So we are looking at the vinylic carbon. If the vinylic carbon has 2 hydrogens, the product would be carbon dioxide. If it only has 1 hydrogen, we produce a carboxylic acid. And if it has no hydrogen, we produce a ketone. We could actually have this in an intuitive manner. Let's try to cleave this up. Alright. So here, what do we get? We get this half, right? And at the other half, we get this. Generally, these hydrogens are what you call oxidizable, simply because these hydrogens, if oxidized, will be replaced by oxygen. If you have two hydrogens, the carbon will not be bonded to two oxygens, but instead it will be bonded. This carbon will be bonded to an oxygen with two bonds. So what do I mean? So if we have two hydrogens here, I said it will not be replaced with two OHs. No. What happens is that this carbon would be bonded doubly to an oxygen. Here, this is a blank area. Since it is two bonds, then it would do the same. Alright? Also in this case. But look at this hydrogen. This is just one hydrogen. So, the rule is, if the oxygen can replace only one hydrogen, it would exist as OH. But again, if the oxygen can replace two hydrogens, it would form a double bond with a carbon. So look, what did I say? If the vinylic carbon has two hydrogens, how many hydrogens do we have here? Two hydrogens, right? How many hydrogens do we have here? One. So as I have said, we have a product of carbon dioxide if we have two hydrogens in the vinylic carbon, and that is correct. And what do we have here? We have CH3COOH. This is acetic acid, right? This is a carboxylic acid. This came from this one, which is this rule, right? So we are correct. From a half with one hydrogen, we are able to yield a carboxylic acid. In this case, acetic acid. How about this one? We now know that this one is supposed to yield carbon dioxide. How about this? Since we have two carbon-to-carbon bonds here, these cannot be touched by oxygen because they are stable. So what happens is the remaining two blank bonds are occupied instead. And what is this? RC double bond OR. That is the general structure for, guess what? A ketone. In this case, this is acetone. Did we get it correct? This one has 0 hydrogens on the vinylic carbon. We have 0 hydrogens, we yielded a ketone. We yielded a ketone, right? So this is correct. So that's the general rule for oxidative cleavage. And generally, that's without certain special cases of reactions. Those are the general reactions for alkenes. And we will see that alkynes actually have the similar kinds of reactions. So let's try drawing ethine in this case. Ethine. Let's try to add hydrogen. Alright? So if we add 1 mole of hydrogen, then what's supposed to happen is you're going to remove only 1 pi bond. Alright? 1 mole to 1 mole. But in most cases, this reaction is very quick, very efficient, that you use 2 moles if you're going to use only a metal catalyst. So in this case, you'll fully saturate it with hydrogens and come up with an alkane. But if you want to achieve an alkene out of an alkyne, you must be able to use a certain catalyst, and they call it the Lindlar catalyst. So again, if you want to produce an alkene from an alkyne, you must use a Lindlar catalyst and 1 mole of hydrogen. So that's it for hydrogenation of alkynes. Now, what if we have a mole of halogen in the presence of a certain solvent such as DCM? Well, again, just like in alkenes, we produce a vicinal dihalide. Alright? And if you add another mole, you fully saturate it, but this time you have a lot of chlorines instead. Now, what if you use an asymmetric reagent such as HCl? So if you use 1 mole of HCl first, what happens? Again, let's copy CH, double bond. One would have the H and one would have the Cl. And this is a common mistake of people. If you add another mole of HCl, some of them would add the Cl to the other to say in order to balance it out. One carbon would have one Cl and one carbon would have another. But again, let's remember the Markovnikov rule. If we have another HCl here, where should the H go? To this carbon with more H or to this carbon with less H's? Yes, if you answered this carbon, you are correct. So actually, if we add another mole of HCl, what we would get is this. We follow the Markovnikov's rule, right? And the Cl will go to the carbon already with a Cl. So what do we get here? We get a geminal dihalide. Alright. Now, another reaction. How about if we hydrate it? The presence of acid. In alkynes, they add another reagent. Alright, HgSO4 or mercuric sulfate. Here, what happens is, as usual, we copy, then we add the H to one and the OH to another. But here you would see that this is an alcohol, yes, because it has an OH, but at the same time it is also an alkene. And in this case, you form an enol. But actually, an enol is unstable because look at this. Oxygen, it likes electrons. It's electronegative, but it only has one bond with carbon. As compared to this carbon, it has two bonds, and oxygen will be like, hey, I'm electronegative. I should have more bonds than the carbon. So what happens is that it rearranges. What happens is that the O will get the double bond and the carbon will get the single bond. And so actually what we get here is an aldehyde or a ketone. And we get here the aldehyde, the keto group or the carbonyl group. That's why you call such reaction or such rearrangement keto-enol. There's a certain term for it, and that term is called tautomerization. And in this case, you could say that this enol and this aldehyde are tautomers of each other. Alright? And finally, we could have also strong oxidation. So again, that is KMnO4 in the presence of acid. Same rules apply, no? So for example, we have H here. By the way, there is a difference. So if we have here two hydrogens in order to produce carbon dioxide, if we have alkanes, we just need one. We just need one. And if we have no hydrogens, we produce already a carboxylic acid. We cannot produce a ketone from from alkynes. So since these ones, what do we follow? One hydrogen. Both of these carbons have one hydrogen, so we would say that the product is 2 moles of carbon dioxide. Now let's go further. Let's try to elaborate or verify the strong oxidation rules for alkynes. So again, 1 hydrogen yields carbon dioxide, 0 hydrogen would yield carboxylic acid. Then let's have an example just to make sure. If you're still wondering, you want to be sure of what we are talking about here. So here, let's try to cleave this. What are our two halves? So this is the first half, and our second half is this. I said that 1 oxygen would consume 2 bonds to form a double bond with carbon. So what happens? So if we have 3 bonds, then we could use 2 of this to form a double bond O, right? And then we have another left one, and we say that if we have just one more bond that can be occupied by oxygen, we will just represent that as OH. Correct? And however, you have another hydrogen here, and that would count as another blank bond. So we would merge that and form another double bond to O. So we form carbon dioxide. So we have confirmed this already. Now we have this. So we do the same thing. We use this to form a double bond O. Right? Let's put the CH3 here. And well, look at this. We only have one left. So we use that as OH. Can this OH be double bond O? Can we use this? Of course, not anymore because the carbon-to-carbon bond is strong. So what do we get here? RC double OH. So this is a carboxylic acid, right? And I just said that we yield a carboxylic acid, and so that verifies it. Finally, the last reaction of alkynes is what we call formation of an acetylide ion, because we get the name acetylide from acetylene, which is the common name of ethyl. So here, if we add a certain reagent and we call that a sodium amide, NaNH2 is called a sodium amide, the Na will go to the alkyne. Na. Between Na, or between sodium and carbon, the more electronegative one should be carbon, and the sodium and and all other metals should be much less electronegative. What happens in this case? Look, carbon would be the one with a negative charge. I mean, for the first time, carbon had a negative charge. I mean, for the rest of the reactions we had before, right, we had carbon with a positive charge. So this is a first. So Na has a positive charge here. Now, if we have Rx, X is any halogen, what happens? Halogen should be partially negative and the R here should be partially positive. What happens? Where does the X go? Negative, positive, right? And this is positive, partially positive, it goes to the negative. So what happens as a result? The carbon would bond to the R, and of course the Na, or the sodium, would bond to the X. So this is our main product. So simply what we get is a longer chain alkyne, because imagine if the R contains 2 carbons, we add 2 carbons to the alkyne chain. If the R has 5 carbons, we add 5 carbons to the original alkyne. So sometimes they use this reaction in order to lengthen their carbon chains. Alright. And by the way, since the first to react here is a nucleophile, which of these? This one. This is a nucleophile. This would first take away the sodium before the R would occupy the carbon. That's why this reaction is nucleophilic. But what's the format? This is like AB and CD. Then we just exchange them, get the clue. That is, yes, if you answer substitution, you are correct. This is nucleophilic substitution. So this is the only reaction of alkynes which is not electrophilic addition. Because remember, alkynes and alkenes react by electrophilic addition, but in this case, this is the only reaction that undergoes this mechanism, which is nucleophilic substitution. And that is the last reaction for alkynes and generally for all unsaturated hydrocarbons.